Good morning, CCTI Pre-Calc. Mr. Bashar once again. As we wind down the school year, this is one of the last video lectures, not too many more after this. We embark on a pretty big topic in Trig, which is the identities in Trig. And anybody going on the calculus next year at CCTI, the AP Calc course that I teach, or calculus in college, at the community college level or for university, you'll be expected to know certain identities in Trig because they'll be mixed in the calculus. So in the very beginning of the Trig topic that we started last month, we looked at a couple fundamental identities, and we'll recover that today. Hopefully you'll remember some of that. Also, to any seniors watching, I would just like to mention that you essentially are now done. Your last assignment is due today, Wednesday. But I do want to wish all the seniors luck. I was very privileged to be able to teach all of you guys this year at CCTI. I really did enjoy having you in class, and as I said in the email, there's no doubt in my mind that you guys are leaving the course with much more knowledge than when you came in. And it's nice to see everybody grow, and the underclassmen too, of course. But for you seniors, you really did grow a lot. You really stepped up your game this year to take my class, and I appreciate your efforts. And I appreciate your efforts as time winded down with this coronavirus going on and the online learning. It wasn't necessarily easy. That's the least to say. So I wish all you seniors luck. I'm sure we'll get to communicate before graduation as well. So today in this video, this will be helping specifically the juniors that will be going on the calc next year. And if you're going in the probability, it doesn't matter. It's still, good knowledge to pick up here in Trig. In the textbook, this would fall actually section 6.1 if you're following in your textbook. If you're doing the Khan Academy like I assigned, you can think of 6.1 as everything that you see in Khan Academy. But we're going to start out with a problem actually that we kind of done before, but now it's a little bit different. So here's the problem we're going to start out with. We're given that sine of theta is negative 5 over 13, and theta ranges between 3 pi over 2 and 2 pi. So what does that mean? Well, let's go to the coordinate plane and think of this. So we're in radians here, of course. Angle theta is between 3 pi over 2 and 2 pi. So that means the angle has to be somewhere down here in quadrant number 4. So if we rotate, we're going to be somewhere down here. Right? So this will be your angle theta. And technically on the inside, that's theta prime. But we answer only to theta here. So we have to figure out the remaining trig functions based on this knowledge that sine is negative 5/13 and theta ranges between 3 pi over 2 and 2 pi. So there's a couple ways you could do it because you've seen something like this before. I like to look at it in terms of absolute values because you have a negative here, but when you square that, it's going to become positive, right? And oftentimes if we try to fool around with the signs too early in this game, we get confused. So I'm going to treat this problem as like an absolute value, and we're going to look at just the positive sides of the triangle. We're not going to worry about negative. We'll let our brains figure out what the sign has to be. So, if you remember, sine's ratio is y over r. So in your right triangle, so here would be your right triangle, the long side is r, up and down is y, and left to right is x. So I'm going to think of this as y over r. So that means your y is really negative 5. But we're going to look at this in terms of the absolute value of negative 5, which is positive 5. And our r is 13. So that means we have to figure out what is x. And that's not so bad because we're going to use the Pythagorean theorem. X squared plus y squared is r squared. Okay, now I'm going to use the values. We've got x squared, we don't know, plus y squared, so we're going to use the 5. It doesn't matter if you use the negative 5 because when it becomes squared, it becomes positive. But this will be 25. And then r squared, That's 13 squared, which is going to be 169. So you got the equation x squared plus 25 is 169. That means we got x squared is 144, and that means x is 12. Now technically it's plus or minus 12, but since we're concluding that we're going to use the absolute value here, we only want the positive answer. We don't want the negative one. If you're working with the negative sign, you have to actually stop here and figure out, is this x positive or is it negative? And that causes problems. So let's just consider the positive case, and we'll figure out the sign as we go forward. So here you go. So you have x is 12, y is 5, and r is 13. So now we could go ahead and do these ratios. So cosine, for example, is given as x over r, right? So x we found to be 12, r is 13. So now we have to ask ourselves, is cosine 12 over 13, is that going to be positive or negative? Well, remember where you're located. You're down here in quadrant 4. Remember that jingle, all students take calculus? Cosine and its reciprocal secant are positive down there. So this is a positive 12 over 13. We can also find secant, because secant is going to be just the reciprocal of this guy, right? Let's see if I can turn this. There we go. So secant is going to be 13 over 12. No work required. How about, let's find cosecant. Cosecant is the reciprocal of sine. So if sine is negative 5/13, this has to be negative 13/5. Again, cosecant is definitely negative down in quadrant 4. And we need tangent. So what's tangent of theta? Well, tangent is given by y over x. So y is 5 and x is 12. And then we just have to ask, what is the sign going to be? Well, tangent is certainly negative down here in quadrant 4, so this is negative 5/12. So you see, it's easier to let your brain decipher what the sign is at the end. And then, of course, if we want cotangent of theta is going to be negative 12/5, because it's strictly just the reciprocal of tangent. Okay? There you have it. So again, you've done this problem before, just a little bit different the way that this is represented to you. But this is a very important thing. We use this in calc a lot when we're working on problems to figure out what the sign is going to be and stuff. And all that stuff with reference angles, that all still comes into play. So this might be a good place to pause maybe before we move on to some of the identity part. But this should be kind of a little bit of a review from the past. Okay, so now we're going to look at some fundamental trig identities. These are things you got to know. You can find these in any textbook. These are time-tested identities, and we use them over and over in calc. So I'm just going to review some of the identities we have. And you'll know these in your sleep. We have the basic things. You got to know the reciprocals, right? So sine of theta is 1 over cosecant theta. Cosine theta is 1 over secant theta. And tangent of theta is 1 over cotangent theta. Now tangent can be written as sine theta over cosine theta. And as you'll see in some of the examples today, that's very important to be able to rewrite in those fashions. Okay? And then we could also go backwards. Like, for example, if you're given cosecant theta, you can write that as 1 over sine. If you're given secant theta, you can write that as 1 over cosine. And if you have cotangent, you can write that as 1 over tangent, which would then be, in turn, cosine theta over sine theta. we have what we call a Pythagorean identity. Sine squared theta plus cosine squared theta is 1. That is huge. From this, I in the past derived this. I won't derive it again. But we have tangent squared theta plus 1 is secant squared theta. And we've got cotangent squared theta plus 1 is cosecant squared theta. Very important identities as well. The good thing about trig is an awful lot of stuff we can do comes from just these few identities here. So there's a lot that we could actually do just based on these formulas that you see here. And as time goes on and problems get a little more complex, we'll pick up a little bit more identities that we need. But for now, this is pretty good to have in your toolkit. So we'll proceed with some of these today and see how far we could get. One of the big things you got to do with these things is use them in problems so you can simplify. For example, oftentimes in trig that we see in calc, we want our answers to be written in terms of sines and cosines. We don't necessarily like writing in terms of secants and cosecants and cotangents. You know, we like to keep it at sine and cosine. Now, sometimes you can't just write everything in terms of sine or cosine, right? But we try to. So I'm going to give you some examples here where we have to be able to apply these identities. Because in calculus, a lot of times, we may be given an expression, a trig expression, that is kind of complicated. We do not want to necessarily work with it that way if we don't have to. So here's an example. We have tangent cubed of x times cosecant cubed of x. And what we want to do here is go ahead and simplify this. So that means we want to be able to break it down as far as possible. So a good place to usually start is, you know, rewrite these things in another way. So for example, tangent can be thought of as sine over cosine, but it's tangent cubed. That means we have 3 copies. So that means we would have sine cubed over cosine cubed. So we got sine cubed of x over cosine cubed of x times, now we'll do the same game here. You have cosecant cubed, sorry. So that means you're going to have 1 over sine cubed. That's the reciprocal identity, right? And you see what magic happens here. The sine cubes, they wipe out. So you're left with 1 over cosine cubed x, which is good. But if we don't want to keep the fraction, we can write this simply as secant cubed of x. So you see that expression up there actually is equivalent to a simplified version called secant cubed x. So you see how we kind of use the rules that we have to simplify. Okay, that's the idea. Let's look at another one. Say we have the following. We have cotangent of x times secant of x times cosecant of x times sine squared x. So there's a lot going on there. But again, we want to kind of apply the same principle as over here. Break these things down. For example, cotangent of x can be thought of as cosine x over sine x. And secant of x can be thought as 1 over cosine x. Cosecant of x can be 1 over sine x. And sine squared x, we're just going to leave that right there for now because we want to see what we can do with it. Now look at some of the things that happen. The cosines cancel out. So on top you're left with 1 times 1 times sine squared, which is just sine squared x. And on the bottom you have sine times sine. So what do you think sine of x times sine of x is? Well, if I asked you what's x times x, you would say x squared, hopefully, right? Especially at this point in the year. So this is actually sine squared x over sine x times sine x, which is also sine squared x. They cancel out, and your answer is just 1. So this whole nasty expression actually reduces this to the value of 1. that thing represents the number 1, which is kind of cool. As you know, there's many ways to write 1. 1 over 1, 8 over 8, negative pi over negative pi. And now we can write 1 as cotangent times secant times cosecant times sine squared. Kind of interesting. Okay, so this is basic ones. Now let's look at when we have fractions involved. So for example, what if we have something that looks like this? Sine of x times secant of x over tangent of x. So that's nice, right? Whenever you see a fraction, we hope that we could get rid of it, right? I think we can do that here. Sine of x, nothing we could do. Now, secant of x, we could think of that maybe as 1 over cosine. So let's try it out. By the way, it's not always a guarantee that this may work on the first time. And tangent of x is sine of x over cos x, like that. Now on the top, sine of x times 1 is just sine x. So we got sine x over cos x. And on the bottom, we got sine x over cos x as well. And right there alone, you should see what that is. Something divided by the same something is always 1. But if you want to be proper, you could call this tangent of x over tangent x. And that would also give you just 1, if you want to be a little more proper. But once again, that expression reduces to the number 1, which is kind of cool. Well, I think it is anyway, but that's just me. So that's how something like that works. So again, you're seeing the fundamental identities being over and overly used. That's the whole idea. All right, so how about one, let's see, how about one like this? We have cosine to the 4th. So cosine to the 4th x times tangent squared x over sine cubed x. And we want to simplify that. So there's a lot going on. Notice the exponents are a little bit higher, right? So you got to be cautious to remember that we have multiple copies of things at this point. So let's see how we can think of this. Well, cosine 4th x, let's not try to do anything with that quite yet. So I'm just going to write it as cosine 4th x. Now tangent squared, right? Now tangent, remember, can be written as sine over cosine. But if it's tangent squared, that means we have to write it, if we're going to use that ratio, we want to write that as sine squared over cosine squared. And on the bottom, I'm not going to do anything. I'm just going to keep it as sine cubed. Now you see what happens here. You have the cosine 4th to the x being multiplied, and then you have a cosine squared. That means we can get rid of this whole cosine squared out of the bottom. That drops this to 2. So you have cosine squared over sine squared divided by sine cubed. Just like that. And now, you could get rid of both of these sine squareds and be left with one sine in the bottom. So you've got cosine squared x over sine x. And I think this is all we're going to be able to do, perhaps, right? For now, anyway. Because we can't call this cotangent quite yet, right? So this may be where we want to stop. But think about some of the other things we know. Cosine squared x is part of that Pythagorean identity. I'll tell you now, it's not going to help you here. But what would happen if we kind of stretch this out and call this cosine x times cosine x over sine x, like this? You see what I did? I pulled them apart. I could write this as cosine x over sine x times cosine x. And what is cosine over sine? That's cotangent. So that's cotangent times cosine. So we could actually write it this way without the fraction as well. Cotangent of x times cosine x is actually the same thing as saying cosine squared x over sine x. So technically, which one's the more simplified? This one right here. Is it better than this? It's in the eye of the beholder. In my personal opinion, no, because nothing was able to cancel out here, unfortunately. If it was, then it would be the better of the two deals. Okay? So this may be a good place to pause before we go on to the next problem, which requires fractions and combining fractions, which you guys don't like sometimes. So let's pause here, and I'll do one more problem with you. Okay, the last problem is going to require a little bit of ingenuity here. But this also happens a lot. So here's one like this. We have cosine x minus 1 over sine x minus sine x over cosine x minus 1. Only if that thing was a multiplication problem, this problem would be done lickety-split because everything would cancel out. You know, diagonally. Doesn't happen since it's a minus. So just like in algebra and in like arithmetic, if you're dealing with adding or subtracting fractions, you have to get a common denominator in order to do so. So that's going to be our first step. So our common denominator simply is going to be this guy times this guy. So we got sine of x times cos x minus 1. And now we have to even up the numerators. So cosine x minus 1 has a factor of sine x, but not cosine x minus 1. So we're going to have cosine x minus 1 times cosine x minus 1 minus, now the sine x has to be multiplied by sine x because it doesn't have that factor. So again, all trigonometry aside, this is the practice we've done in arithmetic and in algebra. So now I'm going to go ahead and multiply. We're going to use classic FOIL. And that's kind of the cool thing in Trig. You could still actually use your classic FOIL technique and multiply. So that's going to give you cosine squared x, because cosine times cosine is cosine squared. This will be negative cosine x and negative cosine x, which gives us minus 2 cosine x. And negative 1 times negative 1 is a positive 1. Okay, so that's just using FOIL. This over here is going to be minus sine squared x, because sine times sine is sine squared, and we apply the minus that's floating out in front of the bracket. Okay? So you may want to go back over that yourself and see if you could untangle all that, but that's just actually basic algebra type stuff. Okay? That applies to Trig. And of course, we'll write our common denominator, which is sine of x times cos x minus 1, just like that. Okay? Now, this is where you got to be kind of creative because there's a lot going on here. There's no more like terms. We can't put anything together. We can't cross anything off. But what I'm going to do here is regroup this problem. And this is one of the problems with Trig, until you master the thing, is that you have to use intuition sometimes. And I know that's kind of a cop-out for me to say. What does that mean, Mr. Bouchard, intuition? The more problems you do, you kind of just see what's going on. And what you have to see here is that you have a cosine squared, a sine squared, and a 1. And all of those float in those formulas, the Pythagorean identity formulas. Remember, we have sine squared x plus cosine squared x is 1. So we're going to use that idea to get us through this problem, right? So for example, if I put the cosine and the sine squared together, it could be 1, but it's not because of a sign problem. It's minus and we need a plus. However, if you would drag the sine squared over to the other side with the 1, that would become 1 minus sine squared x. And if you have that, that means you have cosine squared x. See, that's going to give you cosine squared x equals 1 minus sine squared x. And what that does is, that allows us to replace this with cosine squared x. So here we go. We're going to have now cosine squared x minus 2 cosine x plus cosine squared x over the common denominator of sine x times cos x minus 1. Okay? So hope you followed that. This whole thing right here becomes this guy right here, cosine squared. And now we have some good news because we could combine cosine squared and cosine squared to give us 2 cosine squareds. So we've got 2 cosine squared x minus the 2 cosine x over sine x times cosine x minus 1. So now we're cooking, right? Now we're making some progress. Okay? Let me turn this way. And then guess what? We're going to do something else that you guys don't like, which is factoring. I have a 2 cosine squared and a 2 cosine. So that means I'm going to pull out a 2 and I'm going to pull out a cosine. And when I do that, I'm left with cosine x minus 1 over sine of x times cosine x minus 1. And now you all should be salivating because now this is all multiplication on the top, all multiplication on the bottom. So guess what? We could legally chop the cosine x minus 1's out of there. I'll have to come up here now. That gives me 2 cosine x over sine x. But wait, there's more. Cosine x over sine x is cotangent. So that means our final answer is 2 times cotangent of x. And you're in like Flint. So you see that in this problem, this was great. We had to use a lot of stuff. We had to use a lot of algebra stuff, arithmetic stuff, and the new trig identities that we've just learned this year back in March. Okay? So, I think this is a very good place to stop. If you can handle a problem like this, overall, you're in good shape to understand the basics of trig. So, I'm going to do one more video with you coming up probably tomorrow, and that'll help the juniors get through the rest of their Khan Academy stuff. Until then, Mr. Bashar here, hoping you have a wonderful day. Get outside, get some sun. The weather's been really nice. We haven't been getting no rain, which is good. And I'll see you guys next time.